Hello everyone, thanks for joining. This is Dr. Lim. As AI permeates our work and daily lives today, the use of GPUs have broadened, not only for training massive models, but also for real-time inference, such as voice assistants, video understanding, and robotics. GPUs are working across both cloud and edge. There's one question we need to address. Why is accelerated computing necessary? You have probably heard of LLMs, so or these language models like ChatGPT and Gemini that you use often. LLMs work auto-aggressively. Given the input context, they predict the next word one at a time. High performance always comes with a cost. Inference of large-scale models draw power and generate heat. So, especially at the edge, not only responsive but performance per watt becomes crucial. So here's today's plan. On a Jetson Orin Nano development kit, we'll learn the same LLM under identical conditions and compare text generation speed in token per second when using CPU-only version versus GPU-only version. Then, on the same device, we will change only the power mode to see how speed scales with power. Finally, as a hands-on project, we will demo a wearable voice assistant using a glasses-style Bluetooth headset to experience firsthand why accelerated computing matters in real life. To the main topic, we will proceed with the Llama 3.1 8 billion Q5KS, the largest model we can run on the Jetson Orin Nano we have. The goal of the experiment is simple. When we ask an LLM a question, we will compare how much difference there is in answer generation speed, tokens per second, between CPU and GPU mode. First, to ensure fairness, we fixed all conditions. Llama CCP, CUDA build, context length -C is 1024, prompt batch, micro batch are 16 and 8 each, generation length -N is 512, threads -T fixed at 1, and the prompt used the same sentence. The Jetson's power mode is 25 watt and cooling is fixed at 70%. Measurements are taken after one warm-up run. Now let's run them one by one. Okay. We will run CPU only mode. The thing you should know about is set all layers to run on the CPU, which is set -ngl to 0. Okay, you can see, you can monitor the usage of CPU and GPU and memory in JTAG batch. You can see the number 1, 2, 3, 4, 5, 6, which is multi-thread of CPU. So only single core is running because we set the number like that. Running on CPU is really slow. Okay, we stop the running on CPU, and the token generation speed is 0.64, which is very slow. In this time, we are going to run the model on the GPU. You should change the dash NGL number 0 to 999. So we are going to run fully. We are going to run the model fully on the GPU. How is it compared to before? You can immediately feel visually that it is much faster. We can check evaluate time, and token generation rate is 8.86 tokens per second. That's about 13 times difference. Why does such a difference occur? The core computation of large language models are large-scale matrix multiplications and attention. These operations inherently require broad parallelism and high memory bandwidth. CPUs have relatively narrow parallelism and limited memory bandwidth, so bottlenecks easily arise in initial weight loading and layer computation and KV cache preparation. In contrast, GPUs massively parallelize this process with thousands of compute cores and high bandwidth memory. That's why the first token arrives faster, and in the subsequent loop, the compute cores stay well utilized, keeping tokens per second that is the token generation rate high, very high. Especially as prompts get longer, outputs get larger, and in scenarios where real-time performance is critical, like voice assistant, video understanding, and robotics. This gap becomes even more palpable. Since we confirmed the GPU's advantage in parallel operation in Project 1, let's now explore its efficiency more deeply. When running AI on edge devices, performance is inseparable from power. The concept I want to emphasize here is the energy delay product. In short, EDP. EDP is the product of energy consumption and delay. The lower it is, the more energy efficiently the system provides fast responses. Simply put, the key is to use less energy while finishing the job quickly. First, let's note the design difference between CPU and GPU. CPUs are specialized for general-purpose computation, strong in sequential instruction processing, and complex branch prediction, but limited for parallel tasks. Conversely, GPUs are optimized for large-scale parallel computation with thousands of small cores and handle data flow quickly with high bandwidth memory. This difference is why, as we saw in Project 1, the GPU is more than 13 times faster. So, how does the GPU behave as we reduce power from an EDP perspective? Through DVFS, which is dynamic voltage and frequency scaling, the GPU lowers clock speeds and uses clock gating to turn off unnecessary cores to save energy. The priority is to stay within the power budget. It sacrifices some parallelism but optimizes KV cache and memory access to minimize the increase in delay. As a result, EDP stays balanced, maintaining practical performance even in lower power modes. Now let's run the experiment. The Jetson Orin Nano supports 7 watt, 15 watt, and 25 watt mode. Taking the GPU 100% off-roading at 25 watt from Project 1 as the benchmark, we change only the power mode with the same Llama 3.1 8 billion instruct Q5KS model and prompt conditions. The prompt is the same as before to observe the answer generation process. To explore efficiency, we will focus on token generation rate, which is token per second, across varying GPU layers off-roaded, as shown in the comparison graph and table. The graph illustrates how token generation rate changes with the number of GPU layers off-roaded for each power mode. Green color is for 7 watt, blue for 15 watt, and red for 25 watt. Efficiency increases with more layers off-roaded to GPU, with the lines rising accordingly. At full off-roading condition, which is 33 layers, the 25 watt mode reaches around 9 tokens per second. 15 watt hits around 6, and 7 watt achieves around 2. The accompanying table details the values per GPU layer from 0 to 33. At CPU-only mode, which is GPU layers set to 0, is 0.46 token per second in 7 watt, 0.71 in 15 watt and 0.64 in 25 watt. Values rises as layer increases. For instance, at 17 layers point, you can see 0.75 in 7 watt and 1.25 in 15 watt and 1.14 in 25 watt. At 33 layers, which is GPU only mode, you can see 2.25 tokens per second in 7 watt mode and 5.88 in 15 watt mode and 8.89 in 25 watt mode. In 25 watt mode, efficiency peaks at 8.89 tokens per second with full offloading, so the answer is generated quickly and completely as you see. But energy consumption is large. In 15 watt mode, efficiency reaches 5.88 tokens per second at full offloading, so answer generation is slightly delayed, but the content is completed the same and the real-time response is possible. EDP, which is energy delay product, is more balanced, improving battery efficiency. In 7 watt mode, efficiency is 2.25 tokens per second at full offloading, so answer generation is noticeably delayed, but the final answer content is the same. EDP is optimized on the energy side, making it suitable for long battery-powered operation. Through this comparison, we see that Edge AI optimized the power-performance balance using EDP with efficiency varying by power mode and GPU offloading layers. In Edge AI environments, constraints on battery and real-life performance are significant. Real-time performance are significant, so EDP-aware design, tailoring offloading, and power mode is essential. And it plays a key role in realizing on-device AI, such as wearable devices. Now that we have confirmed the superiority of GPU parallel processing in Project 1 and Project 2, and the importance of the power performance balance considering EDP, we will apply this to an actual wearable device. The true value of Edge AI is realized in real-life applications. In today's hands-on project, we will implement an on-device voice assistant by combining a Jetson Orin Nano and a glass-style Bluetooth headset. The software implementation is as follows. For ASR, we use the faster Whisper library to accelerate the Whisper model on the Jetson. Whisper is transformer-based, and the GPU's parallel processing increases the speech frame processing speed by more than 10x. Input audio is captured in real time from the headist microphone, and VAD, which is voice activity detection, is applied to filter noise. Next, for the LLM, we adopt the Llama 3.1 8 billion Q2K from Project 1 and apply 100% GPU offloading using a CUDA build of llama.cpp. The prompt uses the ASR output text as context, and in the token generation loop, it streams to TTS upon sentence completion. We will use Piper for TTS. The entire pipeline is integrated into a Python script, and each module is executed in parallel using multiprocessing. Now let's start the demonstration. I'll put on the headset and say, please tell me about NVIDIA's CUDA. Please tell me about NVIDIA CUDA. First, when running in 100% GPU mode, the ASR instantly converts the speech to text. Then, the LLM generates token as high speed on GPU, allowing the response to stream rapidly, sentence by sentence, just like this.
CUDA is a programming model created by NVIDIA to allow developers to use the GPU for general purpose computing. It provides a set of libraries and tools for
the TTS synthesize this and play it through the headset, and the entire process completes quickly. Thanks to the GPU speed we confirmed in Project 1, a smooth and natural interaction is possible. Conversely, if we switch to 100% CPU mode and test the same query, the response is up slowly and sequentially, one word at a time. The total time taken for response generation becomes very long, making real-time conversation very difficult. Let's see the result.
CUDA C. Compute unified. Device architecture is a parallel computing platform.
Through this contrast, we can truly understand and feel the practical value of GPU acceleration. Through the Jetson Orin Nano project, we saw the overwhelming performance advantage of GPU, accelerated computing, and the importance of EDP-aware power performance tuning. In Edge AI, these techniques deliver real-time responsiveness and energy efficiency together, enabling everyday on-device experiences like wearables. As AI sink deeper into our world, accelerated computing is not optional, it's essential. Thanks for listening.